Hey everyone, and welcome back to this series on single variable calculus, and today we're going to be continuing our exploration of applications of integrals for single variable functions. So what we're going to do is we're going to look how integrals can be used to solve problems in the basic world of economics. Obviously these problems are going to be simplifications of actual real-world problems because real-world problems usually have multiple variables in play simultaneously, right? But the main idea pretty much creates a framework if you want to sort of extend this or generalize this a little bit on. So the main two principles that we're going to be building a lot of our calculations on are called the law of supply and the law of demand. So first off, you start off with some good that you want to sell, for example, a book or a car, something like that, right? So that's going to be the good that either some people are going to buy or a company is going to produce or make. Right? So the law of supply says as the price of that good increases, the quantity of that good that suppliers offer is also going to increase, because if it's more expensive, we obviously want to save more. But on the contrary, the law of demand says as the price of a good increases, the quantity demanded of that good from consumers is going to decrease. Because obviously if something is only worth $20 and, for example, the cost of that is like $25, a lot less people are going to buy it because the value and the cost don't exactly match, right? So usually what we would like is the cost to be less than the value to us, but the value depends on many people differently, so this is usually hard to balance. All right, so mathematically speaking, what does that mean from the perspective of the law of supply? So the law of supply is told from the perspective of companies, and the law of demand is told from the perspective of consumers. And what it says is the law of supply for companies, what we're going to do as price increases, we're just going to make more. And from the perspective of consumers, as price increases, we're just going to buy less. So if we think of this from the graphical perspective, so on the horizontal axis, we're going to have quantity, and on the vertical axis, we're going to have price. And the same thing over here, we're going to have quantity on the horizontal and price on the vertical. So as price increases, quantity is also going to increase, for which we're going to supply from the company perspective. So the supply curve is usually going to be increasing. That is, as we go from left to right, we're going to be increasing. Whereas on the contrary, the law of demand says as price increases, quantity demanded is going to decrease. So this is going to have an inverse proportional relationship. So as Q increases, P is going to decrease. So we're going to have this curve. So what we're going to have is two curves. I'm going to represent this as PS of Q, and this is going to be PD of Q. If we assume that the supply price curve and the demand price curve are smooth and differentiable, then we can immediately create differential relations that dps dq should be a positive quantity at any position q, or for the most part, most of those positions q, and dpd dq should be negative for either all points in the domain of PD or ideally most points in the domain. Right? And this is under the assumption that these curves are differentiable. Obviously, if they're not differentiable, which in the real world is common, then we would obviously do some derivative approximations, for example, finite differences and so on. Right? So we have the supply curve on the left and the demand curve on the right. So we have the supplier and the consumer, which usually are going to be independent, or one can assume, but that's not going to be practical. So obviously our goal from the business perspective and also the consumer perspective is how to balance these two perspectives. Right? And what do we want to balance? Well, if the price is too high, what kind of issues will you have? Well, obviously the consumer will not buy any quantities, and therefore, when the consumer doesn't buy the things that producers make, obviously the suppliers have what we call a surplus. And a second scenario, if the price is too low, then the consumer's obviously going to buy them because everything is so cheap, right? So in that case, all consumers, ideally, all consumers will buy if they can, but most of the time the suppliers will run out of stock, and therefore they're going to have a shortage. And neither of these are going to be ideal, right? So what we have to do is consider both these curves simultaneously, because obviously we don't want either of these issues to occur. Right, so what curve goes up? Well, that's going to be our supply curve. And what curve goes down? That's going to be our demand curve, right? Supply goes up, demand goes down. So where these two curves cross, under the assumption that they do cross, but if we assume that the supply curve is monotonically increasing and the demand curve is monotonically decreasing from minus infinity to infinity in terms of the ranges, whatever that means, then they're going to have at least one intersection. Right, so there's going to be this point here where in some sense everyone is happy, both the supplier and the consumer. And this point is what a lot of economists call the equilibrium point. Right? And associated to that equilibrium point, we have this ideal quantity Q star. That's how many things the companies will make. That's how many things these consumers will buy. And this price, P star, is the price for which they will sell and or be bought at. Right? So this equilibrium point, which is Q star, P star, is the ideal value for which we usually search for in the economic world. Also keep in mind, these curves usually also depend on time, so these curves usually shift over the course of time. So usually these aren't fixed quantities with respect to time, they usually change. But let's assume that this is going to be true for a particular fixed time, or stays the same for all time t. The next concept that I want to introduce is what we call the consumer willingness to spend. Because obviously when the price is really cheap, consumers are willing to spend a lot of money to buy many of those quantities. But when the price is really, really high, usually we want to buy less. So consumer willingness to spend is going to depend on which curve, supply or demand. This is obviously going to depend solely on the demand curve. All right, so let's take a look at that demand curve again. So again, does demand curve go up or down? So quantity, price, the demand curve goes down. Right? So this is going to be P, D, Q. But keep in mind there is also a supply curve in this particular picture, and hence there exists some equilibrium point right here. Right? So let's assume that this is our Q star, and let's also assume that this is our equilibrium point, P star. Right? So if we choose to have let's say some quantity Q located here for which somebody is willing to buy, then there should be an associated price to that quantity located right here. Right? So this price here, so this is what we refer to as the maximum price a customer is willing to pay for that quantity. Let's call it Q naught. Right? So that's going to be the price, P naught, for which a customer is willing to pay for that quantity Q naught. And keep in mind this value of Q could be located anywhere up to Q star in practice, and it obviously is going to be associated down to 0 if the price is really, really high. So therefore, if we were to shade in all of these possible regions, then what we're going to have is this region located here. Right? So this is what we refer to as the customer's willingness to spend. And let's also make one other quick note before we give the calculus definition. So keep in mind, even if a customer is willing to pay more, they will only pay P star of the when the market is at equilibrium. P star when the market is at equilibrium. Right? So what we're looking for here is technically this value here, if at equilibrium. That's going to be how much the actual consumer spends, which we refer to as consumer expenditures. Right? So we have actually two quantities: the customer is willing to spend and the actual value for which a customer pays. Right? So let's define these via integrals. So the customer's willingness to spend, which I'll define as CW, customer's willingness to spend, CW. So let's look at this from the graphical perspective. So again, we're going to have this curve here, and then we're going to have our Q star here. And what we're going to do is find the area of this region. Even though that height value is here, we're still going to be willing to spend, even though we actually might not. So this is going to be the integral from 0 up to Q star of our demand curve with respect to Q. And then we have our actual expenditure. Again, let's assume that this is our Q star. Let's assume that that is our P star. So how much are we actually going to spend? That's going to be this area here, which is going to be less than or equal to the value of CW. So I'm going to call this the consumer expenditure. Consumer expenditure, which I'll abbreviate as CE, let's say. And that's going to be equal to the integral from 0 to Q star of which curve is going to be our demand curve, which is going to be this decreasing curve, or is it going to be a flat curve, in particular the P star constant? And indeed, it's going to be the P star constant, again, with respect to Q. And keep in mind, if P star is relatively constant, then that's just the area of a rectangle. All right? So what is this difference between these two curves? Because keep in mind, we have this Q star, we have this rectangle. So this rectangle is the consumer expenditure. We have the entire area over this region. This is the consumer's willingness to pay. But we also have this region here, which is the difference. So if we were to add up the consumer expenditure plus this area of that rectangle, the consumer expenditure, the area of the rectangle in this shaded red region, we would get the entire willingness to pay. This shaded red region is what we refer to as the consumer surplus. Consumer surplus. And we'll give interpretations of these in a minute. So CS obviously would be CW minus CE, which is, if we represent that in integral notation, the integral from 0 to Q star of our demand curve, P to Q, minus P star dQ. Obviously, you're going to get a negative value if you flip these around, but keep in mind P star is the area underneath, P to Q is the entire area underneath, and with the area between these two curves, and therefore that's going to be P to Q minus P star. So that's what we refer to as the consumer expenditure, consumer surplus, and the customer's willingness to spend. Let's go through a couple little intuitive explanations as to what these actually represent in real life. So I've gone ahead and drawn a little diagram summarizing these three quantities: the consumer expenditure, the consumer surplus, and the consumer willingness to spend, CE, CS, and CW respectively, inside this little diagram where these areas are calculated with respect to the demand curve, which is always decreasing, hopefully. So we have these three scenarios that I have sketched here. If the consumer willingness to spend is too high, if the consumer expenditure is too low, and if the consumer surplus is high, because you should be able to figure out that if CE is low and CS is high, then CW should also be high as a result. Right? So these three are usually going to occur simultaneously. Take a moment and pause this video what you think these mean in the practical world. Here's a couple scenarios that you probably have come up with. If the consumer willingness to spend is too high, This usually reflects a higher perceived value of the product for which the consumer is purchasing. This means that the consumer is going to benefit because there's going to be a favorable market price associated to that. And why is that? Because the cost is going to be too low for the companies, and therefore they're probably going to be increasing the price in the near future. So a bunch of people are going to buy in and get as much as they can. And why is that? Because they're going to be paying less than the willingness to pay, because everything appears to be cheap. This obviously is going to get an increase of surplus for the consumer, because usually people are going to buy Q star of it instead of more of it than they actually need, right? So if you only have 5 cars, or only want 5 cars, but cars are super cheap, you're probably going to buy 50 cars. Why? You don't need 50, you only need 5, maybe, who knows. But you're going to stock up in the expectation that the price is going to increase, and then you're going to turn around and sell them a little bit later on. So from this perspective of the consumer, this is obviously going to give them more benefit for their expenditure because you're buying more for the same exact price in a different market, and therefore this is going to give you a lot of customer satisfaction, and therefore it's going to lead to an economic efficiency, generally speaking. There's obviously some counterexamples that I'm not mentioning here, but this is at least the basic framework for which we could consider. Now, some people would question, well, is it possible that we can calculate the area under the curve past Q star? And the general answer is yes, but the practical answer is no. So I want to just briefly go ahead and talk about that quickly before we get into a quick calculation example using these things for which we've built. All right, so consumers, let's assume that they want to buy under a nice market, Q star. But sometimes can only pay for, let's say, 0 less than or equal to Q less than Q star. So they only can buy less of them because obviously it costs less. Therefore, Q greater than Q star is not considered commonly due to what we refer to as the law of diminishing returns. Right, because you might be thinking, well, if you buy like 50 billion, let's say, houses, and you raise those prices, obviously nobody's going to buy them from you because the prices are just too outrageous, right? And you probably won't even get as much satisfaction because you can't appreciate or value the individual houses if you only had a couple. Again, there's some counterexamples to this, but this is the main idea for which these things are built on. All right. So let's just go through a quick example that works through all the calculations for these principles for which we've laid down. All right. So let's assume that we have a demand curve that's equal to Q plus 2 divided by Q plus 1. And let's associate that the associated supply curve for this market is equal to 0.3 Q. Right? So the first thing that I probably would recommend you do is to sketch out what these curves looks like. So take a moment and pause this video and see if you can give that a try. So obviously if we take the limit as Q goes to infinity for our demand curve, since we're working with a rational function, the limit is going to be equal to 1. So we're going to have a horizontal asymptote of 1 for our demand curve, and that's obviously going to be decreasing since the leading coefficient is positive. All right. So when Q is equal to 0, notice that's going to give us 2 divided by 1, which is going to be 2. So we're going to have a vertical intercept of 2 for our demand curve. So that's going to decrease and approach 1 as Q goes to infinity. So that is going to be our demand curve. And then we have our supply curve, which is aligned with a positive slope passing to the origin. So let's just give that a quick draw. Let's just draw it as this. All right, so that's going to be our supply curve. And we can clearly see where equilibrium is located at this point here. So that's going to be our Q star. And then we're going to have some P star that probably is going to be located somewhere between 1 and 2. Right? So take a moment and see if you can find where that actual Q star and P star value is located. So where do we even start to find where the equilibrium point is located? Well, that's going to be where the demand curve and the supply curve are going to be equal to each other, the Q value that makes them true, for which we usually call Q star. So this is going to be true if and only if Q star plus 2 all over Q star plus 1 will equal to 0.3 Q star. And then we can cross multiply to get a quadratic equation. So that's going to give us 3Q star squared minus 7Q star minus, what is that, 20 is equal to 0. And then you should be able to either use the quadratic equation or factor. This actually factors quite nicely. You can use the AC method, for example, and you can get 3Q star plus 5 times Q star minus 4 is equal to 0. So we're going to have two solutions to this quadratic equation for which we can quickly do via factoring. So we're going to have Q star is equal to negative 5/3, and Q star is equal to positive 4. Under standard economic conditions, the quantity for which we can buy and sell is usually a non-negative number. Therefore, this first solution is not going to be useful to us. Therefore, Q star is going to be equal to 4. Therefore, our P star value is going to be equal to our probability demand curve, or the probability supply curve, evaluated at Q star. So that's going to be equal to, for example, from our linear curve, 0.3 times 4, which is going to be equal to 1.2. So therefore, equilibrium point is going to be equal to 1.2. And we can go back to our previous graph and draw it. So this is going to be equal to 4, and this is going to be equal to 1.2, which is between 1 and 2, as we conjectured before. All right? From here, we can calculate the consumer willingness to spend, the consumer expenditure, and the consumer surplus as we defined them before. So let's go ahead and do that. So the consumer willingness to spend is going to be equal to the integral from 0 to the quantity for equilibrium, which in this case is 4, of Q plus 2 all over Q plus 1 with respect to quantity. So from here we can use long division and write this in standard form as the integral from 0 to 4 of 1 plus 1 over Q plus 1, and we integrate this with respect to Q. This is a very easy integral to do because the integral of 1 is just going to be equal to Q, and the integral of 1 over Q plus 1 is just going to be the natural log of the absolute value of Q plus 1. And then we just need to evaluate this from 0 to 4 and get some value, and then you can find this is approximately equal to 5.6094. From here, we can calculate the consumer expenditure in a similar fashion. So the consumer expenditure, again, will be equal to the integral from 0 to 4 of which curve? Well, it's going to be the horizontal curve, or the P star value, which we found to be equal to 1.2. And we just need to integrate this with respect to Q. So that's going to be equal to 1.2 times the length of the rectangle, which in this case is going to be 4, and that's going to be equal to 4.8. Once we have the consumer willingness to spend and the consumer expenditure, then we can easily find the consumer surplus by subtracting these two. So the consumer surplus is going to be equal to, again, consumer willingness minus consumer expenditure, which in this case is approximately 0.8094. Right? Now, from these little objects, usually we can't get quick interpretations because usually it depends on the market that we're working with. So there's another metric that is referred to as the surplus expenditure, consumer expenditure ratio, SER, which is defined by CS divided by CE, or the consumer surplus divided by the consumer expenditure. From our example, we can find that this is approximately equal to 0.1686. So you should be able to take a moment and think about the fact, do you want this number to be large or do you want this number to be small? I'll give you the answer and let you think about why that is the case, but the larger the better. Now the question then becomes, for a basic economic structure or economic market, how large is large and how small is small? Some say, and of course this is a rule of thumb, and it obviously depends on the market, that bigger than or equal to 0.50 is okay. That is the surplus expenditure ratio. Being arbitrarily large, ideally bigger than 50%, is usually decent. And of course, I'll let you think about why larger is better, and then I'll let you think about why 50% is ideal, at least as a basic framework. So these are just some of the basic things that you can use integrals for from the perspective of economics. Obviously, there's several different, more complicated structures from economics that I'm not mentioning here, but we'll come back to them at a later time. Hope you enjoyed this video, and I'll see you in the next one. Take care.